All right. So it is our pleasure to have Agustin Moreno from Uppsala speak about on the spatial restricted three-body problem.
Okay, so thanks, Igor, and thanks a lot for the opportunity to speak here. So as the title suggests, I mean, I will discuss a bit about the spatial restricted three-body problem. Right? So this is a very old problem, very well known, that has been around for at least 100 years, right, since work of Poincaré and a lot of people after that. So this will be a bit of an overview of what we're actually trying to do. So I apologize in advance for maybe the experts that perhaps would like to see more details. I'm certainly happy to discuss after the talk. So this is based on two papers that I wrote with Otto, so which are available on the archive. There's also a spin-off paper that I wrote by myself on what I'm calling the holomorphic dynamics aspects of the problem, also available. There's also a survey that I wrote based on some lecture notes that I taught in the material. Okay, they're all available on the archive. So having said that, let me remind you what the setup for the very well-known three-body problem is. So we start with three objects, right, which we call the Earth, the Moon, and the satellite, and they have certain associated masses, and we just leave them there to interact with each other according to Newton's law of gravitation. So this is some dynamical system that we're trying to understand. It's a very, very classical one, in some sense the first one. There's some classical assumptions that people have made throughout the last century in order to, well, simplify the situation a bit. So for example, you could look at the restricted case in which you assume that the mass of the satellite is 0. So in other words, the satellite is negligible when you compare it to the other two, which are called the primaries. There's also the circular case in which you assume that the primaries, the Earth and the Moon, they move in circles around their center of mass, as opposed to the more general situation in which they move in ellipses. Right? There's also the planar case in which we assume that the satellite moves in the plane containing the Earth and the Moon. And the spatial case is when we drop the planar assumption. So now the satellite is allowed to move wherever it wants to move. So the goal for us is to study the motion of the satellite under the influence of the Earth and the Moon. Okay. So here's a picture for you to remember. You know, we have the Earth, the Moon, and the satellite, which is doing whatever it's doing. And we want to predict some sort of behavior. Okay, so this is a Hamiltonian problem, right? So because of the assumption that we made on the Earth and the Moon that they're rotating in circles, we can actually choose coordinates which accompany that rotation in such a way that now they become fixed. And the gain for us is that the Hamiltonian becomes autonomous. So in particular, it is a conserved quantity of the motion. And you can actually write it down explicitly. So here it is. So it has some kinetic term. There's a Coulomb potential associated to the Moon, Coulomb potential associated to the Earth. And then the price we paid because of this change of coordinates is the appearance of this angular momentum term here, which keeps track of the rotating coordinates. But now the gain is that there's no t dependence. And here we usually normalize in such a way that the mass of the Earth and Moon is 1. And mu, which is usually called the mass ratio, you can think, after this normalization, you can think of it as the mass of the Moon. So they're basically two parameters in the problem, mu, and there's the Jacobi constant, h equals c, so we fix the energy of the system at c. The planar problem is precisely when we drop the last two coordinates, so p3 equals q3 equals 0. And because of the form of the Hamiltonian, this is actually a flow invariant subset. So it's a codimension 2 invariant subset of the dynamics. So there are some special integrable limit cases already present that we will particularly care about. So one of them is when we set mu equals 0. So you can think of it as the Moon is not there anymore, right? But I still remember that the frame is rotating. So when I set mu equals 0 in the previous formula, I will find that the Hamiltonian H splits into a sum of two pieces. So the first piece is this energy K, which one can immediately recognize as the energy of the two-body problem, where the primary is sitting at the origin. Here you have this Coulomb potential at the origin. And L is the angular momentum term that we had before, which physically keeps track of the Coriolis and the centrifugal force of the Earth on the satellite. Okay, this is usually called the rotating Kepler problem. So it's just a two-body problem, the Kepler problem in a rotating frame. Right? So the solutions to the Kepler problem is just ellipses. Right? This was known to Newton already. He wrote it down in his Principia. Now the frame is rotating, so what we get is like, let's say more generally conics, which are being rotated. They might or might not close up, depending on some resonance condition. There's a fact is that if I take my Jacobi energy to go to minus infinity, after some regularization process, I actually recover the honest non-rotating Kepler problem, the two-body problem. So these are the two sort of limit cases that we will be interested in. So usually one studies this limit cases and then tries to perturb and tries to say something about the perturbed systems. We will actually try to go beyond perturbation methods. So if you do Morse theory with respect to this Hamiltonian, you will find that there are precisely 5 critical points. So L1 up to L5, which are classically called the Lagrangians. This were already found by Euler and Lagrange. Here I'm graphing the energy values of this Lagrangian critical points. So here the x-axis is just the mu axis, so the mass ratio. The vertical axis is the Jacobi constant axis. And so here, for example, you have h of L1, which is the lowest critical value of the energy. So everything that's below h of L1 we call the low energy range. And then you have all the other values, which are ordered. L1 up to L5 is ordered according to the increasing value of energy. So there's some symmetry here in the picture. Everything is symmetric with respect to mu equals 1/2, right? Because the Hamiltonian is symmetric. And here at mu equals 0, you see the rotating Kepler problem, and at minus infinity, you see the Kepler problem. Okay. And the low energy range is especially important for us because it will be the range of energies on which we can actually do contact geometry. So there's this notion also of Hill stability due to Hill, which was working on the same problem around, even before Poincaré. Like people were interested in studying the stability of this, solar system, and in particular, how if orbits can escape or not. So Hill stability basically consists of the following. So you fix of the energy C, the Jacobi constant. You look at the energy level set sigma C, you fix C, and then you might consider the projection to position space. So you take Q and P, you project it down to Q's. The Hill region is by definition just the projection to position space of the level set sigma C. Okay, so this is what they look like, right? So if, for example, if C is subcritical, so if it's below the first critical value of the energy, then you will find that there are actually precisely 3 connected components to the energy level set sigma C. So I'm drawing 2 of them here in the picture. So the first one projects down to a bounded neighborhood of the Earth. There's another one which projects down to a bounded neighborhood of the Moon. And there's also an unbounded one, which I'm not drawing, which projects down to an unbounded component of the plane. So roughly speaking, if you don't have enough energy and you start near the Earth, then you will stay forever near the Earth. The same thing if you start near the Moon. And then if you don't have enough energy and you start sufficiently far away, then you cannot get near the Earth and the Moon, and you're an asteroid. You're one of the good asteroids, right? The bad asteroids are the ones which come and crash the Earth. We don't like those. Okay, so this is a Morse theory in the low energy range. So if you look at the first critical value, L1, this is actually an index 1 critical point. So Morse theory tells you that whenever you cross it, you will have to attach a 1 hand. So this is what you see, right? Whenever you cross the first critical value, if you're slightly above it, then physically you're creating a transfer region. It's like a 2 region. This just means that the satellite now, in principle, has enough energy to do a transfer between the Earth and the Moon. Okay, and you can imagine what the sort of level sets look like for the spatial problem. This is a planar problem. So direction in the fibers is P, the direction on the base is Q. Good, but if you look at the Hamiltonians that we had before, there were some Coulomb potentials. So those are obviously singular at collision. So whenever your satellite crashes against the Earth, so Q equals Z, or you crash against the Moon, Q equals M, conservation of energy will tell you that the velocity needs to explode. So here, in the picture that we had before, this just means, you're gonna crash against the Earth, so you better shoot off to infinity in the fiber direction. So the level sets are non-compact. This might be a tragedy for someone like an engineer, right? You really want to avoid collision orbits if you're trying to put a satellite in orbit, but we are mathematicians, so we don't really care too much. Fortunately for us, there are ways of dealing with collisions. So there's this regularization schemes. One of them is due to Moser. Right? The idea is that if you're gonna crash against the Earth, then you put a trampoline and then you crash and then you come back where you came from. So a bit more formally, the Moser recipe boils down to taking 2 maps. So the first map is a switch map. You take QP, you swap them, and you put a minus in front of the P because you want to preserve the symplectic form. Then you take stereographic projection and you get some new variables in T star 3. So now the point is that you added a point at infinity by a stereographic projection, which corresponds to the collision locus. So the effect of this sort of recipe is that the previously non-compact level sets now actually are compact. So your component, for example, near the Earth gets compactified to a copy of the unit cotangent bundle of S3. The same for the component near the Moon. And then the connected sum component, when you cross the first critical value of the energy, gets compactified to a connected sum of 2 copies of S star 3. So this is the effect of the regularization. Similarly, I mean, this is for the spatial problem. For the planar problem, also gets compactified at the same time. So you will just have to replace S star 3 with S star 2, just a copy of RP3. The same near the Moon, and then connected sum is just a connected sum of 2 copies of RP3. So, I mean, really what you should remember is this picture. I mean, all that's happening is that I am adding a collision locus. So because of the switch map, I should actually think of the velocities as moving on the base of S3, and the positions, which are the q's, as moving on the fibers of S3. And what I'm doing is I'm adding the North Pole, which corresponds to p equals infinity. So with the velocity exploded, I am doing, you know, a real oriented blow up on the primary. I am adding all the possible infinitesimal directions in which I can actually crash against one of the primaries. So this is the fiber at infinity. And well, you should think of this, you know, it's 2 sphere on the fiber as a sort of the component of the level set. Right? There's a regularized Hamiltonian, and the level set also gets compactified. And here I'm drawing this vertical S2 as a planar problem. So I draw it vertically because I also wanted to contain the collisions, right? The planar problem also has collisions. So you should really think of this guy here as an invariant under the flow. It's just a S star S2 sitting inside S star S3 as a flow invariant subset. Okay, so this is all that's going on in Moser regularization. But now, so we have a very nice dynamics on a compact manifold. This is the game. And so after you've regularized, we have this very nice theorem, which in some sense is like the starting point for all the contact geometry that we can do in the 3-body problem on this very old problem. We can try to use techniques that we like and know. So this theorem was proven by a bunch of people in the planar case. So Peter Albers, Urs Frauenfelder, Otto van Kurt, and Gabriel Patanay. This is 2012. Then some students of Otto in South Korea dealt with the spatial case more recently in 2019. So the statement of the theorem, roughly speaking, says that after you regularized, and if you're in the low energy range or slightly above it, then the regularized level sets are contact type. So formally, you take any parameter mu, subcritical C, then the regularized level sets are contact type, and the same is true for the connected sum component. As contact manifolds are actually not terribly interesting. They're just, you know, standard copies. It's just S star 3 with its standard contact structure near the Earth and near the Moon. And if you're slightly above the first critical value, then it's just a connected sum of 2 copies of those. So what's really happening is that this is a critical point of index 1. So I'm attaching Weinstein handle as I cross L1. The planar problem, you should think of it as a codimension 2 contact set manifold, which is also invariant on the Hamiltonian flow, which is now a Reeb flow. Right? So you should think of it as just a standard S star S2 inside S star S3, and similarly for the connected sum. Okay? So in some sense, this opens up the gate of using all the Floer theory in the world that we know, and all the holomorphic curves and whatnot, right? So this is the direction that we're trying to go for, okay? But before I do that, let me go down the years in some sense and tell you a bit about what Poincaré was actually trying to do in the planar problem. So this is a very, very classical story. You know, Poincaré started looking at this problem maybe in the beginning of the 20th century or so, 1910, something like that. And amongst other things, he was interested in finding closed orbits. And this is one of the motivating things why we're actually doing what we're doing today, finding orbits in SFT and for homology and all this stuff.
Sorry, can I just ask a question about what you said before? So just for bigger C, it's just not true that the level set is of contact type.
Yeah, so
is that right?
This epsilon is sufficiently small. We don't actually know how small it has to be. And we don't really know formally whether we lose the contact condition for sufficiently large epsilon, but we do think we do. There's some evidence in that direction. I think one of the students in Augsburg is actually typing some of this. Maybe Urs can say a bit more about that.
Yeah, right. So there is it's not always contact. There is it's close to zero, which somehow corresponds to Monnier critical value. There are contractible periodic orbits of negative action, and so it's no contact there.
Yeah, okay. So we do lose the contact condition if you're sufficiently over the first critical value.
Thanks.
Okay. Any other questions? Okay. So as I was saying, Poincaré was interested in finding closed orbits, and roughly speaking, you can reduce his approach to two steps. So the first step is, well, find a global surface of section for the dynamics. A global surface of section is just a surface embedded in your threefold when you have your ambient dynamics, with the property that the boundary of the orbit is a collection of closed orbits, and such that if you're away from the boundary of the surface, then the orbit of each point intersects the interior of the surface in the future and in the past. So in other words, I put my hand on my threefold, and my hand is large enough in such a way that it intersects all the orbits. And if I can find such a big hand, then I'm in a good situation, because I can consider Poincaré's first return map. I can just follow the orbit of every point, say at the interior of the surface, and then I can look at the first return point, and this gives me a map, right? Which is in some sense, the idea of this is that it gives us a reduction of the degrees of freedom of the problem. We started with some continuous dynamical system on a threefold. We took our large hand and we reduced the problem to studying a discrete dynamics on a manifold of one dimension less, right, on a surface. So now we're doing dynamics on surfaces. And when you consider the return map, by construction, periodic points of the ambient dynamics are just periodic points of the return map. So this motivates the second step. The second step is, well, if you're able to prove a fixed point theorem for the return map, then you're in business because you found orbits. Okay, this is a very classical idea, very beautiful, and it's the setting for the famous Poincaré-Birkhoff theorem. So which says that an area preserving homeomorphism of the annulus that rotates the two boundary components in opposite directions, classically called the twist condition, has at least two fixed points. There's another version which came after Poincaré that says that it has periodic points of minimal period as large as you like, as large as possible, right? So plenty of orbits if you have a twist condition. So the goal for us is to take this two-step approach and try to see what it looks like in the spatial problem. So now we're in 2 dimensions more. We go to dimension 5 before we were in dimension 3. Okay, so this is the goal. So here's a picture for you to remember sort of the classical approach. You imagine that you have a disk-like surface of section, then you have a return map. You might hit it with Brouwer's translation theorem. The return maps always preserve area because of Liouville's theorem. Okay, so you hit it with Brouwer and you get periodic points, which means closed orbits. Similarly, if you have an annulus and you have a twist condition, then you also get periodic points by a Poincaré-Birkhoff. Okay, so this is sort of the classical heuristics, which has survived in many different guises even to this day, as I'll try to illustrate as I go. Okay, so before going there, I need to introduce the notion of an open book decomposition, which is very familiar for people doing contact topology, right? So this is like the global topological approach to the problem. Rather than considering one global surface of section, we consider a family. So an open book decomposition, let me remind you, is on a closed four-dimensional manifold M. It's just a vibration defined on the complement of some closed codimension two submanifold with trivial number bundle B, taking values in the circle. And I want that this vibration is standard in some color neighborhood of B. Namely, if I take polar coordinates on the D2 factor r theta, then pi is just a projection over the angle coordinate theta. So this is a concrete notion. Namely, I have a concrete vibration. This is also determined by abstract data, by the data of a page, which is the closure of a fiber, whose boundary is B, which is normally called the binding of the open book. Then also the data of a monodromy map, which is the diffeomorphism of P, which is the identity at the boundary. And if you give me these two pieces of data, P and Phi, I can cook up for you an abstractly defined manifold M, which we denote by open book associated to P Phi, just by gluing two pieces together, right? A mapping torus piece, the mapping torus associated to P and Phi. Just, take P, take the product with the integrable, glue the top lid to the bottom lid with the monodromy, and then you glue in the color neighborhood of the binding. So now you've closed your manifold. Okay, so the first one is a concrete definition. The second one is an abstract notion. Up to isotopy, they're actually equivalent to each other. For the purposes of dynamics, isotopies are not great because dynamical systems are very sort of sensitive to isotopies. So usually good to work with both notions, right? You will actually want to work with a concrete version if you want to adapt it to dynamics, but the abstract language is also useful to know what the topology is. Okay, so this is a picture to remember. So B here is a codimension 2 subset, which is closed. Then it has trivial number bundle, and a color neighborhood looks precisely like this picture. You know, you have a circle family of pages all having the boundary at B. It looks like as if I took a book and opened it up, and I glued the front lid to the back lid, and then this is what it looks like. And away from this color neighborhood is just a mapping towards some moduli. Okay, so this is the abstract situation. But now this has been a discussion in the world of you know, smooth topology, but now I want to have some dynamics on top of this. So if I have a dynamical system, phi t defined on M, which I assume is generated by some autonomous vector field X, then I will want to say that the open book is adapted to the dynamics if the binding of the open book is invariant under the flow, or which is equivalent to saying that the generating vector field is tangent to the binding. And I want to assume that X is transverse to the interior of all pages. So this should be very familiar if you're familiarized with the notion of a Giroux form, right? This is basically the setting that Giroux considered in his Giroux correspondence. So each page P now becomes what we call a global hypersurface of section. Namely, it's just a codimension 1 submanifold whose boundary is invariant under the flow. So it's an union of orbits, and the orbits of all the points away from the boundary, from the binding, meet the interior of each page transversely in the future and past. Right? So this is just a higher dimensional version of the global surface of section. Nothing deep has happened, but we also have a Poincaré return map in such a situation, just by following the flow. Okay. So as I said, this is more or less classical idea. So let me give you some sort of historical remarks about what people have done with these ideas in the past for the planar problem. So the planar problem has been studied for a long time, you know, smoothly. As I said, after we regularize the dynamics, we shall see a copy of RP3 if we're in the subcritical energy range. RP3 smoothly has the structure of an open book whose page is a D star is 1, and its monodromy is the square of a dangerous along the 0 section. So what I would like is that I should be able to find some concrete open book in this abstract, of this abstract type, adapted to the given dynamical systems in RP3. So, you know, in this language, roughly speaking, you can say that this is what Poincaré actually did a long time ago. Of course, he never said it like this, but we can sort of interpret that he did something along these lines. So using classical perturbative methods. Right? So Poincaré, for example, look at the case where mu is small. So you start with a rotating Kepler problem, which is the integrable case. You perturb it a bit, so now mu is small, and you don't put any more restrictions on C rather than being subcritical. So Poincaré actually finds an annulus-like global surface of section, basically. Roughly speaking, like 50 years later, Conley did a similar thing, but for a different perturbative situation. So rather than taking mu to be small, you can take it to be whatever, but C has to be very, very negative. So you're very, very close to the Kepler problem. So Conley actually also gives us annulus-like surface of section and proves that the return map is a Birkhoff map, so a twist map, and then hits it with Poincaré-Birkhoff and gets plenty of orbits. So he found this long Conley orbits in the planar problem. So if you see, it took maybe like, I don't know, 50 years until someone actually found the orbits in the sort of original problem. You know, Poincaré conjectured his last geometric theorem, this Poincaré-Birkhoff theorem, proved some particular cases of it, and then Birkhoff proved it in generality, but then only Conley 50 years later actually applied it. Just a gap. But then 1969, McGee also gives us disk-like global surface of section for mu small and C subcritical, so the same perturbative case considered by Poincaré, but now replacing the annulus by a disk. And he also computed the return map, used KM theory, found plenty of interesting things. Okay, so this is, you know, bits and pieces of the classical story. These are all perturbative methods, right? We start with an integrable case, perturb it a bit, study what remained. As far as I'm aware, all the non-perturbative methods that gives us something in this problem today are based on foundational work by Hoffer, Wieselski, and Sander. So holomorphic curve theories, you know, holomorphic planes and stuff like that. In this setup, what we usually consider is what we call the convexity range. So the convexity range is those pairs of values of mu and C with subcritical C, such that the so-called Levi-Civita regularization of the planar problem is convex. Now, I didn't tell you what the Levi-Civita regularization is, but you should think of it as a 2-to-1 cover of the Moser regularization. So Moser gives you some dynamics in RP3, then Levi-Civita gives you dynamics on S3, it's double cover. And what I'm asking here is that this S3 should be a convex hypersurface in R4. So if that happens, then I'm in the convexity range. So you should observe that in principle, this is a non-perturbative set of values. So it might be very far from the integrable situation. The integrable situation is just a perfectly round S3 inside R4. So in this setting, using holomorphic curves, all these people, Albers, Fish, Frauenfelder, Hofer, Otto, Van Kurt, in the convexity range actually gave us global disk-like surface of section using all this techniques developed by Hofer and collaborators. Also, there's a result by Klinevich, Salaman, and Vysotsky, also in the convexity range, that it gives us actually an open book on RP3 of this nice abstract form that I find for adapted to the dynamics. There's also a result by Klinevich and Salaman, also the convexity range, who instead of giving us an open book, it's this-like surface of section, but they're actually the pages of a rational open book. So now the open book is not an honest open book, but its pages cover the binding twice, just because you project it down from S3, basically. So as far as I'm aware, these are the latest results in this direction for the planar problem. I might be missing something here and there. So, I mean, I apologize if I am. But so this is more or less, as I understand it, the situation of the planar problem. And you should see that there's a huge gap between the non-perturbative approach and the classical perturbative methods.
Sorry.
Yeah.
What is convex then?
Strictly convex as a hypersurface in R4. So
okay.
Maybe you should think of it. There's a Hamiltonian, and this is like the zero level set of the Hamiltonian, and the Hessian of Hamiltonian should be positive definite on the hypersurface.
Okay, thank you.
And can I ask, so then in the planar problem, existence of periodic orbits is still open in general?
Well, I mean,
is that right?
As far as you mean, like beyond the boundary of the binding of the open book, right? Because the binding of the open books is Hofflin, right? Which already takes some work to find. But then if you also want to find sort of other orbits, as far as I'm aware, we don't.
Sorry, but can you go back one slide? There were some restrictions on the, like outside of the convexity range.
Yeah.
There's
outside of the convexity range, we don't know anything. I mean, what?
There are also some shooting arguments which go back to Birkhoff about retrograde periodic orbits, and this you can do up to the first critical value.
Okay. Any more questions? Okay. So let me state then the first theorem of like one of the first things that I proved with Otto. So this is, as I said, two-step approach in the planar problem. Now we're going to deal with the step one in the spatial problem. So this means finding global surface of section. So what we're going to actually prove with Otto, roughly speaking, is that we actually find globally adapted open books which are adapted to the dynamics in the whole low energy range and slightly above it. And this result in principle does not depend on mu nor c. So this is a non-perturbative result. So formally, you take a compact and kinetic component of the Moser regularized energy hypersurface in the three-body problem. And the theorem is that for any mu and subcritical c, well, you find an adapted open book whose abstract type I write down. So if C is less than h of L1, then the page of the open book is a D star 2, and its monogram is a square of a densidal just. So what you should observe here is that in RP3, we had a D star 1 and a square of a dane twist. I'm just, the higher dimensional version is just replace a D star 1 by D star 2, and the monogram replace a densidal twist, so the dane twist by a densidal twist. Okay. There's also similarly a connected sum formula as you're slightly above the first critical value. And here in both cases, the binding is the planar problem, okay, which is an invariant subset of the dynamics. So the real content of this theorem is that I can find an honest concrete vibration which is adapted to the given dynamics. The dynamics I'm not touching it. You're not allowed to touch it in this setting. So if you're used to thinking in terms of Giroux correspondence, usually you start with some contact manifold. Giroux tells you there's an adapted open book, but in that setup, the contact form is never fixed. Only the contact structure is fixed. So here, it's a different problem, right? So the contact form is fixed, not only the contact structure. But these open books are the one that support the contact structure in the sense of Giroux. So it shouldn't be surprising if you're a contact topologist that this is the abstract type of the open book. Okay, so this is the abstract picture to remember. So here's RP3, it's a planar problem sitting as an invariant subset in there. The pages are a copy of B stars 2, and then the Hamiltonian flow is transferred, so you will have a return map. And now the return map at the Arab preserving condition in the setup is just being a symplectic homomorphism. Okay, so that's a replacement, and that just follows from Lübel's set. And this is like the subcritical C case. So you can imagine what it looks like for slightly above it. Okay, but I want to emphasize again that this does not depend on mu nor C. I mean, this is a very much non-perturbative result. And I mean, at least to me at first, it was rather surprising because this says that finding global subsection is easier in the spatial problem than the planar problem. And one of the reasons is that you already know what the invariant subset is. It's just the planar problem. In the planar problem itself, the invariant subset is this Hopf-link, and finding it is already non-trivial. Finding this orbit, already you need to do something. They're not given to you. In this case, the invariant subset is given to you, just drop 2 of the coordinates. So what I'm saying is that there's a very nice set of coordinates who can actually describe things very concretely. So the step 1 is easier in the spatial problem than the planar. And this generalizes completely the planar situation. I don't think you can actually do any better than what we did, really. And let me give you the basic idea of how you prove such a theorem. As I said, the binding is just drop the last 2 coordinates. So this is a planar problem, which we already know that it's invariant. So this is why we have hopes of finding the open book that we're trying to find. And the idea is really very simple. You should start with pi defined by this formula. So you just put your Q3s and P3s into a complex number, divide by its norm. This gives you an element in S1 defined away from the binding. This has an angular 1 form associated to it, which you can write down very simply. So now what you do is just you plug in the Hamiltonian vector field on d pi, and what you need to show is that this is positive and only vanishes along the binding. This means that the flow is transverse to the pages. And if you do that, you will find very easily that you will get this expression here. So what you should observe is that the numerator vanishes only along B when P3 equals Q3 equals 0. But of course, there's a problem here. Things are not that simple. Is that this obviously does not work over the collision locus. If you have Q equals C or Q equals M, this expression here explodes, right? So this computation in principle does not work over the collision locus. And we do know that it cannot ever be extended this naively to the collision locus. And I'll tell you why. But in principle, this is the basic idea. And this works for any energy. I mean, there's no restriction on the energy for this computation. But first of all, let's try to interpret what this says, right? If you look at what it means, the pi over 2 page is just Q3 equals 0 and P3 is positive. So this just means you sit on the plane and then you start shooting orbits up. And because of, you have these 2 primaries in here, the satellite is going to be attracted by them. So it's going to come down and then it's going to come back up and then down again. So it's going to do stuff like this. So naively, this means that, this page is transverse to the dynamics. But of course, this only works as long as you're away from the collision locus. Right? For example, you could look at the rotating Kepler problem. And in the rotating Kepler problem, there's only the Earth here. And you can imagine like you leave the satellite up here with no velocity. So the guy is going to be attracted by the Earth and it's going to crash against it. And because I regularize, right, it's going to crash, but then it's going to come back up to the original position. So it's going to keep bouncing like this forever. So this is a periodic collision orbit, which we call the polar orbits, over the North Pole and over the South Pole. So you also have the symmetric version bouncing in the lowest hemisphere. But this orbit already tells you that the previous page, quotes, is not transverse to the dynamics, because this guy stays always on the upper hemisphere. It doesn't cross the plane. So this tells you, the existence of this orbit alone will tell you that the previous open book cannot be transverse to the collision locus. So the real work is to try to understand what happens there at collisions. And what we end up doing is we regularize, we find another open book which works over the collision locus, and then we interpolate with this one, and then this creates an interpolation region in between. And in there, you need to really be careful with your estimates. And that's a proof, roughly speaking. So in the theorem that we proved, there's no hardcore technique. There's no holomorphic curves, there's no symplectic homologies, there's nothing. There's just sit down and compute like a mad person. And then by the end of a day, or maybe by the end of 2 years, you will find your open book. Okay, so there's a lot of estimates, but in principle, it's elementary math, but very involved. Okay? This is usually the case in sort of celestial mechanics. Right? But that's as far as I will say about this theorem. Any questions? Okay. So let me tell you what I can prove in general about the return map. And this is as far as I can go with abstract sort of methods. So the theorem that we proved with Otto, also in the same paper, is that you take any mu and then you take some critical C, you fix a page, and then you can prove that the return map, first of all, it extends smoothly to the boundary, which is non-trivial and relies on really sort of a lot of computations in the normal directions to the binding. In some sense, you just need to prove that some Hessian is positive, which is easier said than done. And then what we can say is that in the interior, the return map is actually an exact symplectomorphism preserved in some symplectic form. The symplectic form is just a derivative of the contact form given the dynamics to the page. So this, in principle, depends on mu and depends on C, some contact form. And moreover, and this is really the non-trivial part of the statement, takes forever to prove, and it's actually very difficult because of plenty of subtleties, that this map is actually Hamiltonian in the interior. And the Hamiltonian isotopy extends smoothly to the boundary. So, the fact that this is a symplectomorphism is not particularly difficult. This just follows from sort of general, follows from Lubel's theorem, basically. Here, one of the subtleties in this setup is that omega always degenerates at the boundary because the rate vector field is tangent to the boundary. So you always have a degenerate symplectic form there. But, you can actually write things down in local models in such a way that you can find a continuous conjugation that after you conjugate it, this omega becomes actually sort of a symplectic form at the boundary. This conjugation is not smooth. It's only continuous. Like the map is smooth, but its inverse is not. And this is really annoying. This is also present in the planar problem, by the way. So, some people might recognize this. But after you've done this continuous conjugation, omega becomes the formation equivalent to the standard symplectic form. So in particular, you know what its symplectic homology is. The Hamiltonian here, and you should be careful, the claim is that this Hamiltonian is not relative boundary. I'm allowing to move the boundary around, right? And this is important. This is, in some sense, not terribly different from the planar situation, but this is sort of the higher dimensional things that we can say. Okay, so this is like basic principles, right? So now we might be in a situation in which we can hit it with all the Flow theory in the world and try to use some of the things we know to say something about this map, which in general might be super extremely complicated. Like who knows? I don't know what it does. But anyways, so now basically by construction, you should observe that there are two types of orbits in the problem. First of all, there are interior periodic points of the return map, or there are boundary periodic points. The interior periodic points by construction are in 1-1 correspondence to spatial orbits of the problem of period k. So k here is a minimal k such that you're fixed by f to the k. And the boundary periodic points gives us planar orbits. It's not true that every planar orbit corresponds to a periodic point of the return map at the boundary. And this is good in some sense, but because what we actually want to do is we want to find interior periodic points with arbitrarily large minimal k. This is what we're trying to do because, now we actually want to find spatial orbits as opposed to the planar ones, which were already found before. And I should pause here for a second, because if you're a person that's used to working with symplectic homology or Flow theory and for Liouville domains and so on, usually what you do when you define symplectic homology is you choose your Hamiltonian. Right? You choose it to be small in the interior, you choose it to be linear at the boundary, and then you use some limits and whatnot. And here we don't have that liberty. Right? The Hamiltonian for us is given by nature. I have no idea what it is. It might not be small in the interior. I have no idea what it does at the boundary. And the paradigm shift in some sense is that in the standard situation, symplectic homology detects orbits at the bound, right? The interesting ones at the bound, the interior ones are just critical points. In this situation, there's a difference, right? The interior critical points are also interesting. In fact, they're the most interesting for me. And this is why we really need to have some way of telling apart boundary things from interior things. And this is one of the main difficulties in this set. Okay. So having said that, we move on to step 2 in the spatial program. So now we found an orbits of the section and we want to prove a fixed points there. So for that, I need to tell you what our version of the twist condition is in high dimensions. So the abstract definition is you start with some Liouville domain, you look at the contact form at the boundary, you start with some Hamiltonian symplectomorphism of the Liouville domain. And I will want to say that this guy is a Hamiltonian twist map if I can find a time-dependent Hamiltonian H with the following properties. So first of all, this Hamiltonian should be smooth or at least C2 for all the things that I will care about. C0 or C1 Hamiltonians are not good enough for us. This is for all the people who like Z0 stuff. The second condition is that the Hamiltonian should generate my, my return map F. And the third condition, and this is a crucial one, this is a twist condition, I should be able to find a function little h defined on the boundary and possibly time independent, which is strictly positive and has the property that the Hamiltonian vector field of h, when I restrict it to the boundary, is a positive multiple of the Reeb flow, the Reeb vector field, and the multiple is precisely this function. So in other words, there's a Hamiltonian isotopy, and what I'm asking is that it moves in the positive direction of the Reeb flow at the boundary. And one thing that you should be careful here is that this definition is not localized at the boundary, because I'm assuming that the generated Hamiltonian is globally smooth, or it has some global regularity properties. This is not sort of localized at the boundary. We can actually construct Z0 Hamiltonians which satisfy all of these conditions, but do not, for example, do not have infinite many periodic points. I can tell you a bit about that after the talk. But so in principle, this is the definition. And of course, it generalizes the classical one because the classical case is T star is 1, and it has disconnected boundaries. So moving positively in one direction of the Reeb flow, in both of them, it's just moving in one direction and the opposite one in the other circle, just because of orientations. So the fixed point theorem that we can actually prove with Otto, and this is the most general version that we wrote down, but you can sort of generalize it in several different ways, but we haven't thought of doing so. But the theorem is what we're calling a generalized Poincaré-Birkhoff theorem. Suppose you have an exact symplectomorphism of some Liouville domain, and you look at the contact form at the boundary. You assume a bunch of conditions. So the first condition, F should be a Hamiltonian twist map, which is non-surprising. The third condition is that the symplectic homology of the Liouville domain should be infinite dimensional. For example, a cotangent bundle, or any surface which is not the 2-disk. And the second condition is a technical assumption. So if you're in high dimensions, so if the Liouville domain is at least 4-dimensional, then first of all, we assume that it's symplectic Tel-Aviv because of symplectic homology and grading reasons. And then there's another condition, which I'm not gonna really tell you what it is right now, but it's what we call strongly index definite condition. It has to do with the index, the Conley-Zender index of the orbits at the boundary. They should shoot off to infinity as I iterate. I can give you a definition. There's a slide on which I put the actual definition, but for time constraints, I will not tell you. And in addition, we assume that all the fixed points of F are isolated. So assume all this bunch of conditions, then the conclusion of the theorem is that F has simple interior periodic points of arbitrary large integer period. So you will be able to find plenty of orbits if you can check all of these conditions. So as I said, for example, if you're on a surface, so the second condition is no longer there anymore. What this says is that if you're on a surface which is not the 2-disk, and if you have a Hamiltonian twist map, then you will find as many orbits as you want. Okay, so this assumption is a vast generalization already in the 2-dimensional case of the classical Poincaré-Birkhoff case. For example, if you're in a cotangent bundle, they're all symplectic Tel-Aviv, and then, well, you need to assume the strongly index definite condition. The symplectic homology for cotangent bundle is known to be infinite dimensional, which is the homology of the homology of the free loop space on the base. And then you might try to use this theorem. The strong index definite assumption, as I said, is technical, but it's not as weird as you would think. It's actually implied by convexity. Right? So if you're in the convexity range, for example, in the 3-body problem, then you will have this condition. So the index of the orbits grows to infinity if they are on the boundary, on the planar problem. As I said before, if you're in dimension 2, symplectic homology is always infinite dimensional unless you're the 2-disk. A counterexample to the conclusion of the theorem is rotation, so it's sharp in that sense. This is, of course, a very vast generalization of the classical Poincaré-Birkhoff theorem, and this is, you should really think here Conley conjecture. Right? This is proven in the spirit of the Conley conjecture, as Victor Ginsburg proved it for the closed case, and one of his students, Doris Hein, for the case of cotangent bundles. You can actually use their methods to prove the theorem that I stated before. This is, of course, a very nice and good thing, very sort of closes up very different things that have appeared in our field. The bad thing or the not so good thing about the story is that we couldn't actually check the twist condition on the three-party problem. So on the problem that originated the theorem. And I mean, so at this point, I don't really know if the Hamiltonian twist condition is the right definition, in the sense that I can't check it in the problem that originated the theorem. In some sense, we're at the stage of, where Poincaré sort of said, okay, this should be a theorem, and then someone proved it, and then 50 years later, someone found the orbits. But what we did with Otto is we actually took the integrable case, we computed by hand the return map on the rotating Kepler problem. We could write down the thing explicitly. You can write down a generating Hamiltonian also, but the generating Hamiltonian doesn't twist as we wanted to twist. So this is done in an appendix of the paper that I just updated yesterday and put it on the archive again. Well, this doesn't mean that there's not another Hamiltonian which twists, but I mean, at this point, it sounds rather unlikely. I honestly don't know what to expect. But okay. So having said that, we couldn't really find our orbit. So in some sense, we took our football and we sort of shot from midfield and hit the post with this theorem, but we didn't score, right? But we were nearly there. But because we couldn't do that, there's an alternative approach which actually now does use holomorphic curves on all the holomorphic weaponry that we have at our disposal, and which I'm calling holomorphic dynamics. So this is a paper that I wrote independently. So it's a spin-off of all the story, and it's based on the following observation. And holomorphic dynamics should also maybe called symplectic dynamics in the spirit of Hofer and collaborators. This also fits in their picture of what they're doing in dimension 3 at least. So the observation that starts this new step, let's say step 3, is that the adapted open books that we found with Otto are what we call iterated planar. So this means that we have a fivefold and we have an open book, and the page of the open book is a D stars 2, which admits the structure of a Lefschetz variation with genus 0 fibers. So the fibers of this D stars 1s, and the monodromy is the square of a dangerous. And they all induce the given open book at the planar problem, right? At the binding RP3. So this open book here, just take the boundary on D stars 2. So this is an iterated planar picture that we have. The picture that you should remember is this is a standard Lefschetz variation on D stars 2. It has precisely 2 singular fibers, which intersect the 0 section, which I'm drawing here, in the north and the south pole. The boundary is an RP3 with its standard open book. And when I project down to the 2-disk, what I will see is, well, for example, there's a point which corresponds to I in the plane, to the imaginary number I, which is precisely the famous Birkhoff annulus. So RP3, I can think of it as a unit cotangent bundle of S2. The Birkhoff annulus is I take every vector in the equator of S2, which points up. So this is what I see in the back. And the front, at -I have the opposite Birkhoff annulus. So it's the covectors pointing down. And the boundary of each fiber, which in this picture lie at infinity, so this is the ideal version, corresponds to the Hopf length in RP3. It's just these 2 circles, which I'm drawing here in red. So to get the compact version, what you should do is look at this ideal version and project down in the dual direction. So now they become compact and they have boundary precisely the orbits. Okay, so this is the Lefschetz vibration on the page, and you should think I have a circle family of these guys. Yeah, so more abstractly, and here I'm drawing things as an algebraic geometry would draw them. So I'm drawing the page here as an orange, right? So these guys are here the fibers, F, which I'm drawing in green like the central fibers, right? And the boundary of each fiber is the link in the boundary, so L. B is a boundary which has this open book with the page F and monodromy some phi F, which is precisely the same data of the Lefschetz variation on the page. So this is the page, and I have a circle family of these guys. So This L link, what you should really think is as the binding of the binding. That's the iterated picture. So sort of this is the abstract, sort of the abstraction of the situation. So in this setup, I will prove the following theorem. Oh, sorry, before I do that, here's another picture to understand what's going on. So I have a leftist formation on each page. They all have the same boundary B. And when I project down on each page using the leftist formation, I go down to the 2-disk. Right? But I have a circle family of those, so I move them around. What I see is an open book whose page is the 2-disk. So this says that the moduli space of fibers gives me a copy of S3 with its trivial open book. So in other words, I have a quotient map to S3, and the open book up there, each page projects down to the page of the trivial open book. So here the picture is it's not the best because the boundary is, this circle should be B, but I couldn't imagine of how to draw it in a better way. I mean, if you know, I mean, if you're a better artist than I am, then you might tell me how to draw this better. But you can sort of imagine what's going on. Right? So this is the iterated planar picture. In this context, the theorem that I can prove is the following. So now we abstract the situation. We consider an iterated planar fivefold. So this is a contact 5 manifold with an adapted with an open book whose page P has a structure of a left distribution with genus 0 fibers F and some monitor. Then I will want to look at the space of all adapted contact forms to this open book in the sense of true, but with the property that the restriction to the binding to the 3-dimensional submanifold is also adapted to an open book of the right abstract type. So take the boundary on P. So I call this, like, I don't know, iterated planar Giroux forms for lack of a better name, but it's just adapted to the open book in an iterative sense. Okay, so the theorem in this setting is that not only the quotient S3 will be a manifold, an S3, but also I will actually be able to cook up a contact structure on the moduli space. So the theorem is, if you give me any alpha, which is iteratively adapted to the open book in this sense, I can find for you a moduli space of symplectic copies of the fiber at each page, where symplectic is with respect to the given alpha, so d alpha symplectic, adapted to the given dynamical system. And this fibers foliate M, and at each page they form the fibers of a left variation on each page. This moduli space M is not only an S3, but it's actually a contact S3. So it carries a contact structure psi M, which is supported by the trivial open book on S3. So it's isotopic to the standard contact structure by Giroux correspondence. And the key points here is that if you give me any alpha, I can cook up an induced contact form on the moduli space of curves, adapted to the trivial open book on S3. There's some concrete version of this abstract open book downstairs. Really what's going on here is this picture, all I'm saying is that this picture can be realized by symplectic fibers, where symplectic is with respect to the given dynamics, which I don't touch, right? This is important in this setup. I don't want to touch the dynamics. I want to adapt everything to it. And if you're used to thinking in terms of holomorphic open books in the sense of Hofer-Vysotsky-Zender, all I'm doing is I'm taking one of those Hofer-Vysotsky-Zender type holomorphic open books at B, and I'm upgrading it to a finite energy foliation of a fivefold, which looks precisely like this. So in other words, if you can find a holomorphic open book in RP3, in the planar problem, there's a holomorphic machinery that upgrades this whole foliation to something that looks like this. So in other words, finite energy foliation, so the correct version of the finite energy foliation in this dimension should be this iterated planar foliations. Okay. Good. Let me give you an idea of how you actually cook up such a contact form on the quotient. So the idea is just fiber-wise integration. So as I said, I have this, where is it? Here, this quotient map to the moduli space. All I'm doing is I'm integrating my contact form along the fibers, so along the holomorphic curves. So the contact form or the quotient is as follows. So you stand on U, which is a holomorphic curve, say, and you look at the tangent vector along to the moduli space at that point, which is a vector field along the curve satisfying some linearized Cauchy-Riemann equation. Then I look at the derivative of alpha restricted to the image of a curve, which is a symplectic form or an area form on each element in the moduli space. And all I'm doing is I'm integrating my original alpha along the curve with respect to this area form. This is a one form on the moduli space, and the claim is that it's actually a contact form, which is non-trivial, but it follows because I understand precisely what my foliation is. So it has a Reeb vector field. And it's defined by, in principle, 3 equations. So the first equation is just saying that this vector field is tangent to the moduli space. So it satisfies some linearized Cauchy-Riemann equation. The second and third equation is what the equations that you get if you want to define the Reeb vector field, right? So integrating along the fibers should give me 1. Integrating the derivative and contracting with this vector field should give me 0. What really is happening here is that you should think, if I have an integrable case, if I have, for example, the geodesic flow on S3, which is round, this is a very, very algebraic situation. In general, if you look at these equations, the original dynamics satisfies the second and third equations because it does so pointwise. But it might not satisfy the first one. In other words, the original dynamical system might not preserve the leaves of the symplectic foliation. It might sort of move them around, but it might not send an annulus to an annulus. This is a very special thing, right? That means that it's a flow on the moduli space. If you have that the original dynamical system is a flow on the moduli space, it's a very rigid algebraic condition, which only happens, for example, if the contact manifold is Sassakian. So if the Reeb flow preserves a complex structure. There's a very sort of rigid thing, which you can only expect to happen in an integrable case. In general, what you will have to do is take your original Reeb vector field, project it down to the tangent space of the moduli space, so that now it becomes a flow on the moduli space. And this is the Reeb vector field on the quotient. So it's just a reparameterization of a suitable L2 projection to the tangent space of the moduli space. So in principle, I changed the dynamics. I changed the original dynamics in such a way that now it preserves the moduli space. So in some sense, it's a best approximation with the property that it preserves its foliation. I don't know how much I changed my dynamics, but in principle, this might give me something, as I'll try to explain. But now you're in business, right? You can start playing games with this thing. For example, this is one of the games you can play. You take a page with its Lefschetz variation, and here's L, the link, the boundary. And you can, for example, you take your return map F. You could take, for example, a symplectic disk, a section of this Lefschetz variation, and try to understand what the return map is doing on the sections. So you map it with F, you get some weird disk, which is also symplectic. You get also another symplectic foliation on the image, and you might try to sort of extract some information from this. L is actually fixed because there's a bunch of orbits at the boundary. And with this, I could, for example, cook up a return map on the moduli space. I can stand on the page, this 2 disk on the moduli space, and I can sort of take the section, go up to the 2 disk, map it with F and pull it back down. This gives me a return map downstairs. This might not preserve area because this disk might, do some really funny, strange things. But perturbatively, it actually does preserve area. So I actually use this idea in the paper. So this gives you, for example, if you have a fixed point downstairs, this gives you a fiber which intersects itself. So in other words, it's an orbit of a point which starts at a fiber, it comes back to the same fiber. So you detect that by fixed points of some map on the moduli space. This is what I call a symplectic tomography, where you can just take your tomograph and start sort of slicing your page, and then different disks will give you different return maps. So this is one of the games that you can play. Here's another game, which is what I'm calling the shadowing cone. This is something I came up with conversations with Umberto Pinevitz. So the shadowing cone is, rather than averaging over the fibers and get a moduli space on the quotient, dynamics on the quotient, I can just directly project down all the vector fields. So here's the picture. The Reeb vector field originally is transverse to each page. When I project it down, I might not get a line, I might not get a flow, but it does open up to a cone structure, which is the shadowing cone, just the projection of the quotient map with the kernel of the alpha. If you zoom in over a page, this is what you see. So you see the page of the open book on the moduli space, you see the contact structure on the moduli space, and the cone is transverse to both. And the Reeb vector field, the shadowing Reeb vector field, is the average direction in the shadowing cone. It's just, sitting in the middle, just because by construction, because I integrated along the fiber. Orbits of the original thing, your satellite might be doing some crazy nonsense here, which you don't understand, but you project it down, you get an orbit of the cone. It also does some crazy nonsense, but you might have more hopes of understanding something. So this is like the very beautiful sort of geometric dynamical situation in the problem. Globally, what you can define is this holomorphic shadow map. I start with the alpha adapted upstairs, and I project it down to a contact form in the moduli space. For example, you could ask what happens in the integrable case. The rotating Kepler problem actually projects down to the Hopf flow. So, or for example, if the geodesic flow of the round metric on S3 projects down to the Hopf flow, this is the integrable situation. In the rotating Kepler problem, you can actually find a symplectic sort of lattice variation on each page, which is preserved by the return map. It's a very sort of special thing. And the return map actually fixes the two nodal singularities, and those two nodal singularities correspond to the polar orbits. So one of the polar orbits is bouncing up in the upper hemisphere, the other one in the lower hemisphere, and those are detected as the singular fibers, the singularities in the fibers. The map actually is a classical twist map on the fibers, on the angle. So this actually ties up very beautifully with the classical story. You can prove the following theorem as well. I'm calling this Reeb lifting theorem. This holomorphic shadow map is actually surjective. So what this tells you is that you give me any dynamical system on S3 adapted to a trivial open book, I can find a ray flow on my fivefold, which projects down to that guy. So you can think of that as some complexity statement. So this says that Reeb dynamics on the fivefold, on S2 times S3, say, is at least as complicated as Reeb dynamics on S3. I mean, you can realize any given ray flow on S3 adapted to the open book as something on the fivefold. So the new program here, step 3, if you want, is that, well, we know a bunch of things about dynamics on threefolds, especially on S3. People have looked at them for a long time. Now we can actually try or hope to lift what we know from S3 to the fivefold by pulling back via the shadow map. And I mean, I'm probably already over time, but let me sort of tell you what the case of the three-body problem is. So in the convexity range, Hrivnevik, Salaman, Vysotsky gives you this adapted open books for the planar problem. If you combine it with our open books with Otto, this tells you that the associated contact form is iteratively adapted to the structure. So in particular, it has a shadow. So here's what it looks like. So convexity range is some subset of the low energy range, which contains integrable situations. So it embeds into the space of iteratively adapted contact form, so you can project it down to S3. The integrable fiber is everything that projects down to the Hopf flow. For example, the rotating Kepler problem. And then as you move away from the integrable situation, then you move also away from the integrable case in the quotient. Yeah. So let me tell you further direction which fits into this philosophy of trying to lift what's going on in S3 to the fivefold. This is joint work with Humberto Hrivnevik and Aurora Konopasov. So that has to do with entropy. The claim one is that C infinity generic ray flows on any closed threefold has positive topological entropy, which is something that people have been looking at for some time, for different threefolds. People have proved it for different cases. What we're claiming here is that it should be true for any threefolds, and it's something that we'll actually write it down right now. We're not doing anything very new, which is patching together a bunch of things that have appeared throughout the literature, especially in the dynamical systems literature. But if you have the claim, then in particular for S3, you know that C infinity generic ray flows on S3 have positive topological entropy, and then the hope is that pulling back by the shadow map gives you the same statement on the fivefold. So C infinity generic ray flows on the fivefold should also have positive topological entropy. And here, the entropy should be generated by spatial orbits as opposed to planar orbits. I mean, the planar orbit is invariant. The planar problem is invariant. So if it has positive entropy, then the spatial problem also. But the shadow map, actually, when you project down, doesn't care about the planar problem. It projects down to a circle. The circles are stupid in the sense of entropy. Entropy for dynamics in the circle is always 0. This is telling you something about entropy being generated by spatial orbits. But anyways, let me close with some remarks. Hamiltonian maps, which are not the identity at the boundary, should be studied more systematically, especially in higher dimensions. I don't really know much literature on the subject. If you guys know, maybe you can tell me. The Hamiltonian twist condition, as I said, through it all seems very hard to check. There are some famous examples due to cutoff where it actually tells you that they should be very hard to check. There are counterexamples to the conclusion of the theorem, but they're actually not twist maps, but they're arbitrarily close to the Kepler problem. And so is the three-body problem. So this tells you that there's no abstract scheme in the world that will give you infinitely many orbits, or whatever you actually try to cook up to find orbits should keep the Kepler, the Katok examples in mind, because they only have finitely many closed geodesics on S3. And perhaps this is a good time to revisit the origins. Let's just go back to the original dynamical system with all the tools that we know and try to hit it with fluid theory or holomorphic curves and try to get something new. So thank you.
Thank you very much, Agustin.
This is Sam. I have a question. When you have this global surface of section and you show that there are all these orbits, do you use the properties of the dynamics on the binding to come to this conclusion?
Yes. As I said, I mean, you have this. I didn't define it, but I mean, here's the definition. But if you have convexity, for example, in the planar problem, you have this index growth condition.
So from the index growth, yeah. So okay. So I was thinking some time ago about the following problem. So if you have, say, a star-shaped domain in R2n, and you have a symplectic self-map which is isotopic to the identity, then you would like to say something about fixed points or periodic points of this. And now it's not, let's assume it's not defined on the boundary, but I believe that the dynamics on the boundary is important, because you could sort of, so in some sense, maybe symplectic homology or other invariants on the boundary is important, and the action of that symplectic map on the boundary, even if it's not defined there, because you can approximate from the inside by Hamiltonians, which go up towards the boundary, and the symplectic map has some action on this. So you get some action on some invariant associated to the boundary, and that then, depending how it looks like, it should force to have fixed points inside. So for example, in the simplest case is where you don't have too much choices. If you have an area preserving disk map on the open disk, then there's a fixed point because you can't transport them to the boundary, like in the topological case. In the topological case, you can find a disk map which has a fixed point on the boundary. If you take it away, then there is no interior fixed point, but you can't do it in an area preserving way. And then there seems to be an example by a guy called Neuberger that there is a self map, a symplectic self map isotopic to the identity on the open four-ball without fixed points. But he must have a certain number of fixed points on the boundary, sort of technically. And so I wondered that if there are either too little on the boundary or too many on the boundary, then you must have interior fixed points. So some mechanism like this.
Does he know anything about what's happening at the boundary? Like, he doesn't say?
Yes, he actually constructs it up to the boundary. I think he has 3 fixed points there. So let's assume that his paper is correct. I don't know. It's a very old paper. It's by a guy called Neuberger, Neuberger, and there are 2 Neubergers. He's the son. This is the younger one, and he was the undergraduate advisor of Joel Fish. So it should be easy to find. Yeah.
Okay.
So so it's a self map on the open disk or open four-ball isotopic to the identity, which doesn't have any fixed points, but in some sense it transports them to the boundary. So there are some fixed points there, and I think it's possible that if too many or too little on the boundary, it forces that you must have interior fixed points. So I think nobody really studied this, but we might have the machinery to do so.
But on the other hand, symplectic homology of a four-ball is 0. So, I mean,
no. I mean, you look at the action windows. You have to look. You look at action. Yeah. So I would say you approximate from the inside, then you get. So you look at this family of Hamiltonians. Then, if you have a self map that maps these approximations to itself, you take a direct limit, and you look at what happens on the action windows. And if there's too much or too little going on, then I would conclude, whatever that means, I would expect that there should be interior fixed points or interior periodic points.
Okay, I will have a look at that paper. You say, what was the name again?
Neuberger, Neuberger.
Okay. Good. Okay, thanks.
By the way, great lecture.
Thanks. I hope to see you soon.
Yeah, you will.
I don't know. I mean, if I manage to get across with all this crazy nonsense happening.
All right. Are there any further questions to Agustin?
I have maybe like a general question. You know, I'm not a dynamicist, and it seems first approximation, what people in dynamics want to do is show that there exist periodic orbits and as many as possible. But I guess I wanted to ask, in your opinion, like what is the most optimistic outcome of this, you know, hitting the three-body problem with holomorphic curves? Like, what would be, what kind of information do you think one might, even the most optimistic case, expect to find about the dynamic?
Okay. I mean, sure, as you say, Danny, like the first step in terms of what we learn in flare theory is, well, can you find closed orbits? Then, you know, then comes, you know, can you find invariant subsets? Can you find whatever? I don't know. Like, you know, Hofer does with fish and it's pseudo, like with spheral curves and whatnot. I really don't know. I mean, in some sense, I thought, okay, if not closed orbits, if this holomorphic shadow thing cannot give me closed orbits, it might. You're looking at sort of orbits of a cone structure down there. In principle, you have, you know, multiple different choices of where to move. A closed orbit up there projects down to a closed orbit of the cone, but, you know, not every closed orbit of the cone in principle might come from a projection. So there's already a game that you can play there. Try to sort of maybe input more information, maybe some sort of holonomial representation, which would sort of, you translate from what's going on in the fivefold to the threefold and try to sort of maybe cook up some homology theory that detects orbits of a cone, which come from upstairs. I mean, that's one thing that you could try to do. I'm not saying that will give you anything. Another thing, as I said, is this entropy business. You know a lot about entropy for ray flows or in dimension 3. Maybe you can sort of also conclude the same thing on the fivefold and try to sort of, there's entropy, there's orbits, invariant subsets, or maybe the theory of symplectic capacities has something to say about what's going on upstairs, because, you know, you have a page, say T stars 2, you might try to extract some information from your knowledge of what the symplectic capacities for T stars 2 are. I mean, I don't know. Here's another sort of thing that you could try to, you know, potentially try to extract, is that, so I said entropy, invariant things. I was going to say something, but I forgot. Wait a second, it's going to come soon. But I don't know. I mean, this is the thing that I've sort of had in my mind.
Mm-hmm.
I'm not sure how much you can actually push it, right? And this is all work in progress, if you want.
And then
I think, yeah, Danny. So I think, I mean, not ultimately, but behind, after periodic orbits, you would really like to find closed invariant subsets, and you would like to find orbits which approach those. For example, if they have a hyperbolic structure or some structure around this invariant subset, things which go from one place to the other, and so on. So that would be important. And then, of course, our big dream in the symplectic world, or this kind of things, is to introduce the notion of symplectic fuel and have sort of understanding of satellites who can actually start an engine and have them efficiently run around doing things, scientific missions, with minimal amount of using fuel and in as fast time as possible. So that would be some concrete goal.
Here's another thing, which is, now I came back, what I was going to say. I mean, I told you, I mean, we use symplectic homology for the fixed point theorem, but you could also, you know, try to use what you know about Lagrangians on T stars 2, for example. you know the Fukaya category of T star is 2. There's some, there's some zero section, the fibers. You know what the Rapture homology of the fibers is. And in the case of the three-body problem, the fiber of the North Pole is precisely the collision locus. So, and you know what the Rapture homology of that guy is. It's just the homology of the base loop space on the North Pole. So if you can find infinitely many chords, this corresponds to finding infinitely many long collision orbits. Like this is one thing. I mean, maybe I can find infinitely long orbits that sort of do whatever they do and then they collide. And then they might not collide again. Here's actually the conjecture. I wrote it down, but I mean, it's the same. I mean, I haven't proved it. I mean, I don't even know if it's true, but conjecture is that you should be able to find long interior chords. If you have an exact Lagrangian, which is spin and has Lagrangian boundary and dual domain, and you assume a bunch of things, and if particularly assume that Rapture homology is infinite dimensional, then you should be able to find arbitrarily long chords in the interior. Corresponds to long collision orbits. And this kind of game that you can sort of try to play from stuff that we already know. The problem is always going to be the boundary, right? You don't know what's going on at the boundary, so you need to assume things. Here, what's doing that for us is the strongly indexed definite condition.
Very, very interesting. Right. So I propose that we thank Agustin for his beautiful talk again, and we proceed to informal discussion. Thank you.